Cool. Good morning, everyone, and welcome to How to Write Rust Instead of C and Get Away with It. So Antonio and I are both software engineers at Yelp, and we're here today to guide you through it. So first of all, we work for Yelp. Yelp's mission basically is connecting people with great local businesses. So yeah, let's get started. So first, why are we here? So Yelp is mostly a Python shop, so you can imagine like a user visiting the Yelp website, hitting some Python code, and our use case today would be data serialization. So we rely a lot on the format called Avro, Apache Avro. You can think JSON, but binary with schemas. So you have your user hitting some Python code. We do need to do data serialization in Avro using the official Avro library written in Python. Then we get back the data, magic happens, and you get great reviews for great local businesses. So very quickly how Avro looks like. So as I said, you define a schema. So this is how a schema looks like. You just define it's just a JSON schema that's not going to be inside your data, but just you need it to encode your data. So it's a serialization format. So who says serialization says usually hard on CPU, and it's not where Python usually shines. A quick example of Avro data, if you take this schema with a quick instance, like in JSON, it could look like the first line, and in Avro it's just, bytes. So yeah, quick flash back 2004 when Yelp was founded. It was all Python. Now back to, flash forward to 2018 with the advent like Docker, services, etc. Yelp is still mostly Python, but we've seen some services written in Java, some in Go, some in Rust nowadays. So one of the new use cases you could think about would be, you have a user that visits Yelp and it hits some Rust code at some point in the path. And then you need a Rust library to do data serialization using Avro. You get back the data, magic happens, and you get great reviews for great local businesses. So you can see the scheme coming along, you have some Python code with another library written in Python, or some Rust code, etc., etc. The good thing about Rust is that, Antonio will get you through it a bit later, but it's safe, it's fast, etc. So why stop just here? What if we could get something like this? So yeah, you have a user on Yelp that hits like a Python code. It does data serialization using a Rust library instead, which is faster than Python for doing serialization, hopefully. Magic happens, and then you get great data. Yeah, so that's pretty much it. Before we move any further, let's stop for a second and what you'll bring home hopefully by the end of the talk. So first is, how to write Rust code in Python packages. Why and when would you do that? Some Python, C, and Rust facts, and jokes, maybe. So there definitely will be jokes, but they might not be worth bringing home. So without any further wait, I'm going to let Antonio introduce you to the problem.
So, as Flav said before, from time to time, when we are in production and we're looking at our Python code, we look at the metrics, we look at the application, everything is going fine, but it feels kind of slow, a little bit sluggish. And really, what we want here to do is taking Python from being a snail to be something a little bit faster. If the remote works, great. So the first thing that you should try to do to make your Python code much faster is scaling up or out your application. And that's it, really. End of the talk, we can go home. 99% of the time this is gonna work. Questions?
When it's not gonna work.
Okay, great. We got a smart one in the audience. So from time to time, this is not possible to do because, cost, if you want to spin up 100 instances on AWS, it's gonna be, a bit of a deal. Or your company has other options. Maybe it takes, 10 days to get a server or something like that. So in those cases, you may try to change interpreter. And when I mean change interpreter, I mean using PyPy. What else? So for the few ones who don't know PyPy, PyPy is another interpreter for Python that is going to optimize your code based on, just-in-time compilation, type inference and this kind of stuff, caching. It's very, very good, and it should be your second option as soon as you want to speed up your code. Or maybe you can use the first one and the second one together. They work. But in case this is not enough, then it's time for us to bring out the big guns. And this is the big gun for Python, using the C programming languages. So as you know, Python, the main interpreter, is called CPython and is developed in C. Being in C, you can write C extension for it, meaning that you can actually write C code, compile it, and make your Python application run the C code seamlessly. So just to get a feel on the crowd here, how many people have ever written a C extension? Ooh, wow, nice. How many people like writing C extensions? Yes, you get the hang of it. So nowadays, you'll find a lot of projects, and instead of writing C extensions, they use C types or CFFI, even better. So C type is a module in the standard library, CFFI is a library instead, also developed by the people who develop PyPy and some others. Basically what you can do with the C types or the CFFI library, it's calling via the ABI, we'll go through it later on, functions that are being defined and codified in a C binary. So this way you don't need to fiddle with all the internals of the CPython interpreter. You can just call these external functions, pass arguments to them, and then use the result. And this also works with both CPython and PyPy without much of a difference, and good performance for both, while C extensions are kinda at the moment. And our library, PyAvro-RS, actually uses this approach. The third option that you have is using Cython. Cython is a compiler for Python, and it provides you a superset of the Python language, and basically you can write some code and then it's going to be compiled into C and executed by your application. FastAvro, the library we are going to compare against, uses this approach instead. One thing to remember about Cython is that if you want your application to be fast both on PyPy and CPython, you gotta kind of duplicate your code, because the way you gotta write your code is slightly different, and PyPy is in experimental support, I believe. Anyway, FastAvro does exactly this. It has two versions of the same code, one for PyPy and one for CPython. So since we're going to use CFFI for our code, let me just go very, very quickly through it. So this is basically the code that you need to use CFFI in your application. Basically, you need an header file with the declaration of all the symbols that you're going to use, and the binary file where the actual functions are going to live, and the actual structs. And finally, you can call all the functions or the struct via the object that you just created. As I mentioned before, the trick here is using the ABI. ABI stands for Application Binary Interface, and it's just a set of rules that can be used to make your Python application, or any application really, talk with C functions. So basically it's a way to put arguments on the stacks, to read returns from the stack, this kind of stuff. So basically, as the ABI makes your Python application talk to C, how do we make our Rust application being called from the Python application? Well, what do? It's going to be disguising Rust as it was C, and then we'll make it work. So at this point of the talk, you may ask, yeah, sure, this all works, but this works in C as well. So why should I bother writing Rust instead of C? Well, if you're at this talk, you probably have heard about Rust before, right? Say yes, nod, please. Great. So Rust has, very cool features if compared to C. The first one is guaranteed memory safety. Thanks to the ownership paradigm that is encoded in the language, and the borrow checker and a couple other stuff, Rust guarantees that you won't double free memory, you won't access memory that you shouldn't access, this kind of stuff. And if you ever program C, you know that this is fantastic. The second thing is concurrency without data races. Again, thanks to the very smart compiler the Rust has. Third one is zero cost abstraction. Basically, you only pay for the abstraction you use, and these abstractions are actually much better than C, You have maps and lists and arrays and everything, and they just work. Fourth, model syntax. You have option, result, pattern matching, and many more. And the last one is awesome tooling. Like, I love the tooling, really. Cargo is amazing. If you ever tried Cargo, compiling, installing new application, linting, format, it does everything for you. It's just amazing and just works. Even cross-compilation just works. Now, being this the problem and our approach, I let Flav guide you through the Avro library that we wrote, and that is now used as the main Avro serialization and deserialization library for Rust.
Thank you. Well, let's begin our journey for writing Rust instead of C and embedding everything in Python. So first, we need, well, some Rust code. So first, how to write Avro using Rust. So we were looking on, like, well, we did what anybody would do. We were opening Google and Stack Overflow and looking for a library that was doing serialization and deserialization. We wanted it to support Serde, which is, for those of you who don't know what Serde is, it's a Rust framework for doing, well, serialization and deserialization of any Rust data structure. So you only have to, like, implement a serializer and a deserializer, and it gives you code generation and lots of cool features that you don't even need to worry about because it just works. And last, we wanted a library that was, well, supporting all the specification of Avro, which is more complicated than it seems. So yeah, we were looking through all of this, and we couldn't find any good implementation that was fitting all the parameters. So we did, like any software engineers will do, like when they have free time, we build our own. So this is AvroRS, a library that we wrote, and that does all the things that we mentioned just before. Very quickly, how to use it using Rust. So this is just a test structure. The only thing you need to note here is these two attributes, deserialize and serialize. So these are the Serde attributes, and that's all you need to be able to interact with the library using for this structure. So Serde does all the rest for us, which is awesome. Next, I mentioned in the beginning schemas. So this is the way you define a schema, just passing in a string, and it returns you, like, well, a schema. Now, if you want to write data, you need to well, have something that can write. So a writer, you give a schema to the writer so that the data fits the schema, and something that you can write into. For the purpose of the talk, it's just like vector. It's just this. It's going to be like a byte array. But it's basically anything that you can write into. So it can be a file, it can be a socket, it can be, yeah, anything you can write into. Create a record. There is, like, this is the automated way to create a record. There's a more manual way to create one, like creating a record, putting 27 into A and foo into B. And then you can just append records to the writer and flush it in case. So there's, like, some internal buffering. So that's why the flush is used. So you have Avro bytes now. So now that you have your bytes, you might want to be able to read them and get data structured bytes. So you can create a writer from this reader from these bytes, and iterate over all the records of this reader. And, well, that's all you need to know about, to worry about. So yeah, that's it. So for how to write Avro using Rust, it's pretty straightforward once you have the library. And I'm going to let Antonio guide us through the FFI layer of the presentation.
So, how are we doing on coffee so far? You still awake? Good, because we're going to have more code. So, first thing, if you just remember the library that Flav just showed you like 20 seconds ago, there are two things that we need to expose. First one are structs. So we can expose them in two ways. The first one is defining a struct. For example, we define this Avro string over here, which is basically something that we use for passing smart strings instead of using pointers. And you can define all your attributes in Rust using some weird types. If you ever programmed Rust, usually you don't use star, mut, c, char. I mean, these are raw pointers. Those are just using these FFI layers, foreign function interface. That's what the acronym stands for. And in this way, your user, the user of the library, the user of the FFI library actually, is going to be able to access all the attributes of the structs directory. And also remember to always specify this attribute over here, rep-c. This basically makes the Rust compiler actually encode the struct in a way that can be understood by C application. Otherwise, if you don't want your user to be able to access all the fields in the structs, you can use opaque handlers. We use it a lot in our application as well. So you just define an handler over here, and then you have your internal struct, and you cast your struct when you return it back to this type. I'll show you in a second, actually. So the second to last thing that we need to expose is basically functions. Well, it is pretty easy, but the first time you look at them, so this is called from our library as well, they kind of, they feel a bit intimidating, so let's destructure them. So basically, the first thing that they do is just calling functions that are defined in the Rust library. So this one is the first function that Flav showed you before, is the one parsing a string to get an Avro schema out of it. So what we do in this function is just, massaging a bit the arguments, in this case, dereferencing the JSON pointer, because it's still like a C-like interface, and converting it to a Rust string, and that's it. The second thing we do is doing the same for the result. So what we're doing here is using box, which is basically the Rust correspondence of writing something to the heap instead of the stack, otherwise at the end of the function that will be deallocated. And also here we are actually casting into the opaque handler I showed you before, as you can see. So given this, the signature of the function becomes a little more clear, so you get a pointer to an Avro string, you return a result with a pointer to an Avro schema. The real magic happens in this macro that we wrote, and it basically wraps all the functions that we wrote in the FFI layer. So if we go inside it, basically this is what happens after the macro gets expanded. You'll get a first attribute on top, which is basically the no mangle attributes, just saying to the compiler, hey, please don't mangle the name of my function because I want to access it afterwards. And then adding this to the signature that basically say to Rust, so this is an unsafe function, this is going to be called from C code, and finally basically wrapping the logic that we wrote before into this little util that we called safe unwind. So unfortunately, when you write FFI layers in Rust, since you are basically dealing with C code on the other end, you have some gotchas that you got to take care of. So the first one, and that's why we wrote that method before, it's unwind and safety. Unfortunately, there is no common way between Rust and C and all the other languages, truth to be told, to unwind the stack when there is a panic. So what we need to do is catching the panic and unwinding the stack in the Rust way, so it's clean when the control is given back to the C application calling our library. The second thing are error codes. Since the library is actually gonna look like a C library, then we need to define error codes and a way for your user to get them. And we need to do explicit memory management, because yes, the library is pure Rust, but this little thin layer is gonna be used by C applications, so we need to be very careful in saying to the user what is managed, what is owned, what they need to free, what they don't need to free. Also, we need to duplicate enums, because unfortunately Rust is this shortcoming at the moment. Complex arguments are a bit of a pain. For example, Python dictionary, you need to serialize them, or transform them in some kind of an object, and then feed them into your library, and many more. And this is just, this is too much, really. So, you know what the solution to this? Which one is the solution to this problem? Basically, it's copy-pasting. Go to our library, copy-paste the util function, copy-paste the macro, copy-paste all the util structures, and everything, and you're almost there, 90%. Now, I would like to point you to a decent library instead of copy-pasting, but there is none that I really like, and this is our second project on the FFI layer. So on the third one, we're probably going to write the library, and then I'm going to point you to that. The last thing that we need is the header file. So, as we remember for CFFI, we need an header file with the declaration of the symbols, so we can find them in the actual binary. Now, the header file is going to look exactly like all the definition that I showed you before, but in C syntax. So char star data, this weird uint ptr underscore t, what is that? I don't even have an idea. This type def structs and everything. So, and again, this is a pain, code duplication, other syntax. But you know, we have a solution for that too. cbindgen. cbindgen is awesome. It's a fantastic open source project. You can find it on GitHub. What you need to do is basically just hooking it up in your make file, and with just this little command, will auto-generate the header file for you. It even transforms the Rust doc strings in comments. It's amazing, trust me. Again, copy-paste it, and you're done. You don't need to write an header file anymore. Now that we know how to FFI, Flav, that is our resident Python expert, is going to explain to you how we basically wrap everything into a decent Python library so that the users won't even notice that we are using Rust under the hood.
Cool. So yeah, onto the last step of our journey, Python. So now that we have all the CFFI layer and the Rust layer that we don't even need to worry about now because we have, FFI is what we're going to deal with. The only thing that we have to do is, write C in Python. So yeah, it's not great, but that's how it is. So if you, for instance, want to serialize an integer, you just call the CFFI function value int new and give it an integer, and that's it. As Antonio said, support for complex data structures is not really there. So if you want, like, for instance, serialize a Python list, then you create an array, give it a capacity in the beginning, and for each of the items, you manually append them to the other array, and then you return it in the end. So yeah, just writing C in Python. But Python is a little bit better than C in some cases, and code readability is one of them. So what we did for our library, which is just an example and could be used anywhere, is just defining a small class, and that maps each of the primitive types that Python has, and to a CFFI function. And depending on the type of the value of the data that you want to serialize, just going to call the right function. And it's if you have like a nested value, like a dictionary, it's just going to call recursively. And all the thing that your user needs to worry about is this property in the end, which is value, which is they don't need to worry about anything else. That's they just use the value property, and that's all that they're going to see. So how would it look like as a Python end user? So if you have a schema, you just define a schema using the schema as a string. If you want a writer, you create a writer with the schema. If you want to map a data, you just do it like this. You flash the data, you get the bytes, you create the reader, and for each of the items, you can iterate on them. So that's how it looks like for the end user. It's just Python code. It could be written in Python, it could be written in C, it could be written in Rust, it could be written in anything, and it looks like Python. So yeah, we kind of like it. So now that your users can use your library, you need to find a way to package the library and distribute it to people that want to use it. First, you need the FFI code. So we're just using Git submodules for that. Then every time you have a change into your FFI layer, you need to make sure that you compile it all the time. So the way we do it is using Cargo, which is like the toolbox of Rust, and it can do compilation for you. So every time your code changes, you need to make sure that you run this command. If you want to package your Python package, you need define setup.py and run the commands and everything. So how would the setup.py look like in Python? So that's pretty much how I would look like. The only things that you need to worry about is this package data. So this is stuff that is not Python that you're going to include as well in your package. So you need to make sure that you include the header that Antonio just mentioned, and also the actual binary, Rust binary. You also need to make sure that zip safe is set to false, because when you package Python packages that contain data files, like binaries in our case, they're not zip safe. You just need to make sure that it's how it is. And last, you need to worry about this bdis will. So here it's just a function that, and it's overcomplicated for, it's just, you need to make sure that you compile it for the right, Python version, ABI version, the correct platform, and yeah, it's a pain. You just need to, too many things to worry about. I don't want that. But Milsnake is awesome. So Milsnake is an open source tool built by a company called Sentry, and what it gives you is basically, it's awesome. So let's dig into this. First, they give you like you can specify in setup.py that okay, I have an external something else that I want to build. In our case, it's just a REST package. It can be like anything. Could be C if you want. It could be anything that you need to build. So in our case, you call the command. Next thing we need to worry about is where is the binary? So it's platform independent. You just give it where it should be and how it should look like, and that's it. Last is the header file. So this doesn't change, and it just gives you where the header file is. So in the end, this is how your setup.py would look like. The only thing you need to worry about is adding this, and that's it. You can just build your Python package. It's going to call the REST compilation, and in the end, you're going to have your Python package. So yeah, trust me, Milksnake is awesome. So yeah, now you get a Python package that runs Rust code. But in the end, like, was it really worth it? Was it really faster? Why bother? So I'm going to let Antonio get it for it.
All right. Since we're basically all scientists, engineers, this should be the best part of the talk for us. Numbers, charts, graphs. Let's start. So this is just a random benchmark. I mean, not really a random one. It's a pretty good one for us, but basically, don't focus too much on the numbers. This is just some, encoding and decoding of Avro messages. It's seconds on the left, so the shorter the best. And we can find that our code performs decently well, both on CPython and PyPy. You can see that gets optimized on PyPy for writes, not much for reads, but you get some optimization on PyPy as well, so it works fine. Let's compare it with FastAvro, which is the library using Cython instead of Rust extensions, or we do. So as you can see, like, sometimes they're faster, but we're more or less there. Like, they are comparable. This means that our approach using Rust extensions is comparable to Cython, which is basically, I would say, the state of the art for making C code running into your Python application. Now, this is very important. We actually, for example, deliver much better performances on reads. Who knows why, actually, but we do. And now, just for the sake of it, let's compare both FastAvro and PyAvro RS against the pure Python Avro library, the one maintained by Apache. I'm going to change the scale so it helps you out understanding what's going on. This is the scale. Now, as you can see, on CPython the gains are real. On PyPy, the gains are still real, like less than half or whatever, but as you can see, PyPy really optimizes very well your Python code. That's why, before embarking in this very fun journey of writing Rust, exposing that as the FFI, writing a Python wrapper and everything, or writing CPython, or writing Cython, just try to change the interpreter. Really, do it for me, do it for yourself. And, okay, before to close, actually, I'm sure that inside you really want to know, but I know it's a different language, but how much faster was just the Avro library, the Rust library? Well, it's the red column. Yes. So I'll change the scale again. I'll compare it against only our library. And this is the green column. Yes, Rust is fast. Very fast, as fast as C, basically. To conclude, last part of the talk, since we promised in the title, how to get away with it, which is basically answering to two questions. First one, how to convince my colleagues? Well, Rust is the most loved language in the Stack Overflow survey for I don't remember even how many years in a row. And if so many people love Rust, there must be a reason. Second, compilation just works. Again, cargo is awesome. It just works. Cross-compilation just works. You ever heard of that? Fast recycle. The recycle of Rust is only 6 weeks, if I remember correctly, so you don't need to wait years to see your favorite feature landing in at least the nightly build. and it's a ton of fun, otherwise me and Flav wouldn't be here. Second question, the most important actually, how to convince my company, because you know, they kinda pay the bills. So first one is wheels, compile once, install everywhere, well, given the platform. So in our company at Yelp, what we do for distributing this kind of packages is basically building a Python wheel somewhere in Docker, on Jenkins machines, somewhere, and then installing them on the same platform in production without even requiring a cargo installation or Rust compiler. You don't need to compile any code if you already packaged the build for the right platform. Second is FFI interoperability, and this is a plus that only comes with the C-type CFFI option. So if you write a Rust library and then you package it in FFI, then it's accessible to basically all the languages in the world. Java via GNI or GNA, Objective-C, C++. Actually, at Yelp we have another project where we have some Rust code that is shipped to our website, that is Python, our Android application, and our iOS application via the same mechanism. Rust is as fast as C, which means it's cheap to run, some gains over here, and it's safer than C, so it's cheap to maintain, so, you know, other gains for your company. And finally, is used in production by many companies, Yelp, Mozilla, Dropbox, and many others, probably bigger than yours, so why not try it out? So again, what to bring home? Write Rust instead of C, well, that was easy, it was the title. C binding is awesome, remember that. Milk Snake is awesome, remember that as well. And those are the links for the copy pasting. So remember that we are hiring both London and Hamburg, but instead of going through, you know, the usual shameless hiring plug, I'm gonna tell a story here. So basically, I think it was 3 months ago, I was pretty pissed off, was drinking a coffee with Flav, and I was working on the other project, the other Rust project, and I was like, oh man, I really have a couple cool features that I want to implement, but, you know, there is no good Avro library in Rust, so I guess we're just gonna drop it and wait for someone to implement it. And Flav was like, I see, poor you, poor thing. Then after a couple months, again, drinking coffee, because we do love coffee, Flav comes up to me and say, oh, by the way, I've written the library you needed, you wanna try it out? And so, if you want to work with these awesome colleagues that do your job for you, then come to Yelp. Follow us on any social network too. Top, questions? The screensaver. So, any question? Yeah, we have time for many questions. Yes. Alright, so I don't know how it works for the microphones over here, so...
Just shout your question.
Okay, just talk normally and we're gonna repeat it.
Yes.
Let's do that. Sure.
So I wonder how you do distribution, or do you do distribution of binary packages like wheel format, or do you do source distributions?
No, we just do distribution of wheels, as I said. So we have basically what we usually do for this kind of libraries. We have a Jenkins pipeline, and we do have different Docker containers for the various platforms we are building. And every Docker container installs the right dependencies, you build a wheel. Then we basically upload the wheel to our internal pipey, and users can just install the wheel. Correct. So the question was, how do you do the distribution of these packages? Do you use Python wheels? Do you use something else? You distribute the source, this kind of stuff. Thank you very much again. And that before was the answer. Is that okay? Or does he answer the question?
Yes, and what about macOS?
We do not, yes, what about macOS? We do not ship any macOS code, we just have our iOS library, and for that one, I don't know, I'm not in the iOS team actually. You know what?
Mac Pros. Just Mac Pros that build.
Yeah, you just speak.
We just have some Mac pros that build the thing for Mac.
Next. Okay, I'll just go in order. Oh, we have a mic. Great.
Just to complete the previous question, do you have external dependency when you build a binary library in Rust?
I mean, you could, and yes.
In your case, do you depend on something? Or
No.
is it a standalone?
Yeah. We just use the standard Rust. We don't have any dependency. Really, this is just an encoding and decoding protocol. So it's CPU intensive, a lot of bytes going up and down, but no more than that. For the other project instead, actually, we have external dependency, SSL, and I don't remember what else. What we usually do, it's basically installing them into, well, the machine, or actually in Docker, if it's running Docker. But they're just, dependency installed at the operating system level. We don't package it with the file.
Thank you very much for sharing this very detailed journey. That was very insightful. But the FFI part seemed to be very painful. Now, I'm just curious, why did you do this whole FFI thing yourself, as opposed to using one of the libraries like Pyo3 or Rust, CPython that would do this for you?
That's a very, very good question, actually. So let's take Pyo3, for example. So for anyone who doesn't know, Pyo3, what it does is basically make it possible to call Python from Rust and Rust from Python. And it's very, very similar to the C extension syntax. So you can use it. It's going to work. It's going to actually maybe be even faster than our library. But the only problem is that if you use Pyo3 or this kind of libraries, then you are bound to Python. Instead, with this approach, you can use your FFI package layer in any other language if you want to build a wrapper for that. And in a company like Yelp, where we are actually supporting a lot of languages, even if Python is our main one, this is a very good pro. And as Flav showed at the very beginning, instead of having different implementation of arrows in many languages, they can come with different quirks. We just have one, and everything gets encoded and decoded with the same application. So I guess that's good pro. But yeah, it was a very good question. And there is also another talk about Pyo3. I don't remember which day. Okay, so there was one of the shady advertisements over there. But anyway, good. Go to the talk.
I have mistakes in that. I'm not the author, so.
Any other question? We are free. Yep.
Yeah, you mentioned that you would write a generalized library for the FFI layer for Rust. If you were doing a project or two in the future. So when can we expect that?
Av, how much free time do you have?
Too much.
Soon. Next.
So do you have the same code base for working with Python 2 and 3, or some difference between?
Very good question. It's exactly the same. Yeah. No, we're gonna get the microphone back to the front at the end. Sorry.
From what I have seen, like in the beginning of the talk, you were using the CFFI's ABI mode, right?
Yes.
And according to the CFFI project, at least stating the documentation, it seems like to be the one which is more problematic and also the slowest one compared to the API mode.
Yes.
Did you experiment like with something like generating a C bridge which will compile into an extension so to have some gains?
To be fair, no.
Okay, because from my experience, it seems like that for small functions, the cost of calling it is much higher than, for example, the time of execution of the function itself. So for this ABI mode, you have like the advantage of genericity, so it works like for many languages and not only Python, but especially in Windows, it's kind of very problematic if you have like different tool chains compiled with GCC or MSVC, and I mean your code, which is just shipped with shared object library, I mean on Windows, for example, could not work that easily.
Yes, you're correct. To be fair, we don't target Windows as well at Yelp, so, and I don't own a Windows machine, so I guess I don't really know. But I will try that out. Why not?
How embedded is Rust at your organisation? And I mean, when you decided to use Rust for this project, I should imagine you already would have had a lot of C++ programmers and perhaps experience in C++. Didn't you face a bit of an uphill struggle trying to...
I let Flav answer to that.
Let me. I don't think we have that many C++ programmers at Yelp, or I mean, at least they don't show it, and they, yeah.
So just suggested Rust and that was fine?
I guess so. I mean, we didn't have any, like, we just came in with something that was fast and people were happy about it, so.
Okay, all right.
Yeah.
Actually, I have quite similar question, but more specific about learning curve of Rust, and how much do you like borrow checker?
I love it when my code compiles. All the other time, it's just smarter than me, and I don't like it. But I mean, the learning curve of Rust for, like, I tried Rust maybe 3 years ago, and I didn't like it. It was too hard for me, and then I came back 6-8 months ago, and it's like, it's fine. You just need to take the time, and it's like all the documentation, all the tooling, all the community, everything is great. So you have all the tools to be able to succeed in writing Rust code.
Thanks.
I think we're done. Yes. So if you have any other question, or you just want to offer us a coffee because they're free, just come and talk to us directly. Thank you very much.
Thanks very much.